Welcome to the deep dive. If you've been paying attention to, well, any corner of health and culture lately, you know a quiet revolution is happening.
It really is.
These modern weight management medications, specifically GLP-1 agonists like semaglutide, are just fundamentally changing things. It feels like we've finally found the cheat code to appetite.
That's what it looks like from the outside.
Is it just brute force? Or is this something more, I don't know, a brilliant, coordinated manipulation of our body's deepest biological systems?
That is the perfect question to start with. And our mission today is to really pull back that curtain on how this class of medication actually works.
Not just one single action.
No, not at all. It's a multi-system cascade.
Mm-hmm.
It affects everything from your stomach all the way up to your brain's reward centers.
Mm-hmm.
We've synthesized a ton of information from a detailed literature survey on the mechanism of semaglutide.
And once we get how powerful that mechanism is, we have to talk about the reality check. You know, what happens when you hit the stop button. For that crucial piece, we've distilled the findings from a massive systematic review and meta-analysis on weight regain, which was published in the BMJ.
So we're going to give you the biological how and the statistical what happens next. This is really about understanding the future of treating obesity as a chronic condition. So let's unpack that switchboard.
Okay, so when we talk about how semaglutide works, it's usually just called a hunger suppressant.
Right, that's the simple version.
But our sources make it clear its primary goal is very specific. It's about turning down your appetite and just reducing your overall food intake. It mimics a hormone we all have, GLP-1.
Which is why it's called a GLP-1 receptor agonist. It's basically a very stable, very long-lasting hormone whisperer. It's not like the old diet drug.
Right. It's not blocking fat absorption or jacking up your body temperature.
No, nothing like that. This is an internal communication hack. When it binds to the receptors in your cells, it just kicks off a series of signals that essentially tell your brain, stop, we are full, we are satisfied.
And this is where it gets really fascinating for me. The unexpected twist in how semaglutide even gets to the brain in the first place.
Yes.
You'd think for a drug to act on the brain, it has to get past the blood-brain barrier, the BBB, that fortress that protects the whole system.
But it doesn't, not in the way we usually think. When you inject semaglutide, it largely bounces right off that security system.
So wait, how does it get in then?
It uses these specialized kind of porous access points called circumventricular organs, CVOs.
It's not breaking into the fortress, it's using a secret back alley entrance.
Exactly. The area postrema, the subfornical organ. These are CVOs that don't have that tight BBB security. They're always monitoring your blood chemistry.
Ah, so semaglutide slips through those little windows.
It does. And that allows it to target the brain's master control panel for energy balance, the arcuate nucleus, or ARH, in the hypothalamus.
The appetite switchboard.
Yeah.
And once it's there, I read it uses this incredibly powerful 1-2 punch strategy. It doesn't just turn one thing off.
No, it turns one thing on and the other thing down at the same time.
Okay, break that down for us.
So the ARH has two opposing teams. First, you have the stop eating team. These are the PUM-C-cart neurons. They promote satiety.
Feeling full.
Right. Semaglutide directly activates these guys. It's like hitting the boost button on the signal that says, I'm good, thanks.
And the second action
Up we
on
can.
the other side.
It simultaneously inhibits the eat now team, the MPY-GRP neurons. These are the powerful hunger promoters.
The ones that make you ravenous.
Yes, and it does that indirectly. It uses a middleman. So you're not just boosting the full signal, you're actively silencing the hunger signal.
That coordinated assault, that's why the effect is so powerful.
So powerful. And studies on similar treatments in rats show that these hunger signals stay suppressed. They resist that biological rebound you usually get when you're dieting.
That makes perfect sense for, homeostatic hunger, the actual physical need for fuel. But anyone who's ever stared down a bag of chips knows that's not the only reason we eat. There's pleasure, cravings, reward, the celebratory slice of cake when you're already stuffed.
And that's the next piece of the puzzle. We've talked about the survival circuit. Now let's talk about the desire circuit. This is absolutely crucial to semaglutide's success. Its ability to override the hedonic or pleasure-driven side of eating.
And where does that live in the brain?
It's centered on the ventral tegmental area, the VTA, which is full of dopamine neurons.
Dopamine, okay, the pleasure chemical.
Exactly. Normally, when you eat something really palatable, high fat, high sugar, those VTA dopamine neurons fire like crazy. That's the feeling of reward that makes you reach for one more cookie. It's the neurological basis of a craving.
So the VTA is the part of your brain that thinks chocolate is basically a magic item from a video game.
You could say that. But what semaglutide does is it actively suppresses that VTA dopamine activity when you're eating those foods.
So it turns the volume down on the pleasure center.
Way down, from an 11 to maybe a 2. The food still exists, but that compulsive, pleasure-driven motivation to go get it it's greatly reduced.
I remember seeing a catch here, though. There's a risk of adaptation, right?
Yeah.
The body is smart. It tries to claw back its power.
It does. Early rodent studies showed that while that initial suppression was strong, the animals did recover their appetite for the tasty food over time.
And they figured out why.
They did. That recovery was directly correlated with the restoration of VTA dopamine neuron activity. The brain eventually finds a way to crank the volume back up.
Which suggests this effect might not be permanent for everyone.
Exactly. It could be one reason for weight regain even during treatment if the dose isn't right or sustained.
And it's not just about generalized pleasure. It actually changes how food tastes, which I found so surprising.
It's a subtle but really powerful effect. Patients consistently report they just don't crave sweet things as much, chocolate, starches, that kind of thing. The hypothesis is that it lowers your sweet taste detection threshold. So think of it this way. A moderately sweet cookie that used to taste great now tastes overly sweet, almost sickly sweet.
And that just reduces its appeal.
Absolutely. That little perceptual shift can lead to a huge reduction in eating high-fat, high-sugar foods.
Okay, so we've covered the central command in the brain, the hunger override, and the reward dampening. Let's talk about the periphery now, the physical break.
Yes, the gut's role is absolutely essential here. And the best-known peripheral effect is delayed gastric emptying.
Meaning it slows things down?
It slows the actual physical movement of food from your stomach into your small intestine. It reduces the stomach's contractions and tightens the valve that lets food out.
So your meal just sits there longer, which naturally makes you feel full for hours.
Exactly. That physical presence of food contributes a lot. But there's also a downstream effect called the ileal brake. The ileal brake. See, GLP-1 is secreted with another hormone, PYY, from cells way down in the small intestine. When undigested food finally gets down there, it triggers this brake, which sends even more "I'm full" signal to the brain and slows the whole system down.
And the main communication line for all of this, linking the stomach stretch and this ileal brake back to the brain, is the vagus nerve, right? The body's superhighway.
It is the body's dedicated fiber optic cable. The GLP-1 receptors are actually expressed right on the nerve endings in the stomach lining. They're acting like little sensors, detecting that physical stretch.
And the research on this is pretty clear, isn't it, about the vagus nerve's role?
Oh, it's definitive. In experiments where scientists either cut the vagal nerve or chemically blocked its signals, the satiating effects of peripheral GLP-1 just vanished.
Wow.
It proves that this gut-brain signaling isn't just a part of the story, it's essential. The drug needs that pathway to collaborate with the central brain centers we were talking about. It's a full-body, multi-system effort.
So we've established that semaglutide is this brilliant, multi-pronged biological override, which brings us to the critical reality check. What happens when that powerful pharmacological correction stops?
This is where we have to turn to the hard data, and we're relying on a major systematic review and meta-analysis from a team at the University of Oxford.
Who led that work?
It was led by Sam West, J. Dean Scragg, and Paul Aviard, and it was published in the BMJ. They looked at 37 separate studies with over 9,000 participants.
That's a huge data set. So what did they find about the speed of weight regain?
The findings were, well, they were sobering, especially the speed of the rebound. The average monthly rate of weight regain after stopping any weight management medication was about 0.4 kilograms per month.
Okay.
But, and this is the key part, when they looked specifically at the newest ones, semaglutide and tirzepatide, the regain rate was significantly faster.
How much faster?
0.8 kilograms per month.
Double the speed. That is a rapid slide right back to where you started.
It is. Their model projected that the average person stopping any of these drugs would be back at their pre-treatment weight in just 1.7 years.
A year and a half, basically.
And for these newer, more effective drugs, the ones that cause faster initial loss, the projected return was even quicker. Just 1.5 years.
So the weight loss it doesn't stick around once the drug is gone.
It does not stick around.
What about all the other benefits we hear about? The better health markers, blood pressure, cholesterol. Do those last?
No. They also fade quickly. The researchers found that all the associated cardiometabolic benefits, blood sugar, blood pressure, lipids, all of it, were projected to return to baseline levels within just 1.4 years of stopping.
So the drug isn't curing a condition, it's actively managing it.
And once the management stops, the underlying conditions just resurface.
That speed of reversal is really the key data point here. And it immediately raises the question, how does that compare to, more traditional weight loss methods?
That indirect comparison was one of the most revealing parts of the whole study. The researchers found that weight regain after stopping medication was significantly faster than the regain you see after behavioral weight management programs, or BWMPs.
Not much faster.
About 0.3 kilograms per month faster.
So if you lose, say, 30 pounds through intense diet and exercise, you'll regain it much more slowly than if you lost the same 30 pounds using medication.
That's what the data suggests. BWMP participants were projected to return to their baseline weight only after 3.9 years.
Almost 4 years.
4 years compared to the 1.5 to 1.7 years for the medication group. And this huge contrast forces us to confront a core biological reality that the sources all point to. Obesity acts like a chronic and relapsing condition.
And the mechanism we just dissected explains exactly why. Semaglutide is an artificial correction. It's suppressing your body's powerful underlying dysregulated appetite signals.
And when you remove that drug, those primal signals, the VTA dopamine fire, the ARH hunger switches, they just instantly revert to their baseline state.
The body's programming takes over again.
Immediately. The big takeaway is that these have to be viewed as chronic maintenance therapies, not a temporary fix. And given that real-world data estimates that up to half of all people on these drugs stop taking them within a year.
This rapid rebound is a profound challenge for everyone.
A huge challenge.
Okay, let's try to synthesize this deep dive into 3 core takeaways for you. First, the brilliance of the mechanism.
Right. Semaglutide works through this coordinated multi-system approach. It's centrally suppressing powerful hunger and reward circuits in the brain,
while at the same time peripherally maintaining that prolonged physical feeling of fullness through delayed gastric emptying and that essential vagus nerve signaling.
Second takeaway. The reality check on stopping is stark. Discontinuing these medications leads to rapid weight regain and the reversal of all those health benefits.
And this rebound happens significantly faster than the weight regain you see after behavioral programs.
Which brings us to the big picture takeaway. The success of these medications really relies on sustained, continuous use.
We have really strong evidence now that obesity's biological drivers require a sustained intervention, just like managing high blood pressure or diabetes.
Which leaves us with a final, provocative thought to leave you with. Given that these drugs are so effective because they artificially override these deep biological appetite and pleasure signals,
what fundamental, sustainable lessons, if any, can a patient truly learn about nutrition and movement during treatment that could actually sustain the weight loss after that pharmacological signal is completely removed?
It's the ultimate battle between biological compulsion and learned behavior.
And the answer to that question has enormous implications for public health. Thank you for joining us for this deep dive. If you enjoyed unpacking the science with us, make sure to subscribe.